So my name is Justin Potts. You might see me presenting earlier with Richard. I'm a distinguished engineer and architect for Hedera at Hashgraph, working on a bit of everything, an awful lot of this. And so I'm excited to present to you what's been probably 18 months in the works of trying to solve all kinds of interesting problems and hopefully open a lot of new opportunities for all of you to get access to what the consensus node's doing way quicker and way more conveniently.
A lot of this presentation will be pretty technical, lots of details about the way the block streams are going to work and the way the block nodes work, so should be quite interesting.
Yeah, and I think we'll go into a lot of details. This is all being recorded, so people can always watch it back later. It might take a few watchings to get the whole thing, but I hope that we can create some content that people can reuse and get the idea. So, as of this moment, everything in here is not final. We're still working on all these details. There's 2 HIPs in process, one for the block streams, one for block nodes. I encourage you all to sort of try things out and have a look and contribute to those HIPs. See if it solves problems for you. If it could, be tweaked slightly to solve new problems, brilliant. Let's talk about it. We're continuously trying to improve this. We want it to be the best thing we can be when we first go out with it. So
it's something that'll stand the test of time.
Yeah.
We can define one block stream format and have it really solve problems for a long time to go.
So we're trying incredibly hard to try and make that so that we don't have to tell you block streams 2.0 in another year.
Yeah, we don't want to do that.
so we're trying really, really hard to try and build in everything we want it to be for the future. So how did this all sort of come about? So this came about 18 months ago. I was looking at 2 things. One, trying to explain the consensus node in the simplest form possible. And the other one, looking at decentralization of the data that comes from the consensus node. So this is the sort of 1,000 feet black box view of the consensus node. So, from the outside, we have a consensus node. It gossips to other consensus nodes. It gets transactions from customers, and it produces 4 different streams of data. Not all of those streams are still produced today. One is deprecated. One of them is private, internal, just for backups. And then the one most people care about is records and sidecars. But there's many different bits of data. One of our challenges is that we've got to store, process, and maintain all those bits of data. The consensus node has to do work to produce all of those, to cryptographically sign all those.
Uses up our bandwidth.
It uses up a pile of bandwidth. There's a whole bunch of problems. So where's that data go to today? So that data today goes into buckets on Amazon and Google, and then is consumed by mirror nodes, our mirror node, everybody else's public mirror nodes, and also things get archived away, stored away in a mountain for future reference, so the blockchain's always going to be there for the future. So what does it look like in the new picture? Hopefully a lot simpler. That was really the aim, is consensus nodes take in transactions still, they still gossip with each other, but they produce one stream of output. So the idea is to massively simplify things. And then we've added a new node type, which replaces the buckets as the long-term historian of the network. And the idea is that can be decentralized. The council can run many of those, different council members can, community members can run block nodes. And the idea is to expand that out and have a decentralized network of these nodes. And really that's the big step forward. And then there's a million cool things that came along the way. And then mirror nodes will use block nodes as their source. The other thing that we sort of opened up with it is actually it's not just mirror nodes. Apps can directly use block nodes. Other block nodes can run off block nodes. So there's lots of other different paths for that data and interesting use cases, and we'll go into those in more detail.
Yeah, I think one other thing on there was the streaming. Currently, the way, even though we call it a record stream, we're streaming a full record file at a time. Blockstream gets a lot more stream going, which is also good for reducing our end-to-end latencies.
Yeah, and today it really is a chain of files, and each file is uploaded as a file. There's separate signature files from every node. there's many, many different pieces, and the latency is very constrained by the ability of Amazon S3 and Google buckets to the rate at which they can accept new files and push out new files, and the cost of which of doing that is a massive constraint. So I started going into this a little bit, but why are we doing something new? This is a pretty radical and brave thing to fundamentally change the output of the network. This wasn't something we took lightly. There's got to be a good reason for doing this. So as I said a minute ago, so decentralization was the #1 problem I started out with. And then there's a few sort of sub-interesting problems. So one of them was the cost of running a mirror node. So, Amazon and Google make an awful lot of money by charging a lot of money for their services. It's very expensive to get the data out of buckets. It's both expensive for us to put them in there, expensive to maintain it every month, and expensive for people to get the data out of those buckets. Back when I started this, I think the cost for a mirror node to read all the data was about $20,000 to start up a new mirror node. I suspect it's many times that now. And then the cost per month for reading data out of that was in the several $1,000s a month range. So it meant that you had to have a really good business use case to run a mirror node. We really want to change that so people can start to access this data on a much lower cost point, which hopefully opens up many, many more use cases. So there's also a whole bunch of things that just didn't scale. So like, snapshots, which are backups of the consensus node. Every 15 minutes, we produce a backup of the consensus node state. As we get more accounts and that state grows, it gets more and more expensive to produce those and ship them off to be stored. So having the ability for something else like the block node to be able to produce those save state backups takes all that effort and cost off the consensus nodes.
Yeah, so like if the state on the, like let's say that we have, a half a billion accounts or something like that on Hedera, you might be looking at, a couple terabytes of data, taking a snapshot of that and then shipping it off of the consensus nodes is like a non-starter. Like you can't do that. So in order to get the consensus nodes to the point where we could scale to billions, we have to move some of those tasks off of the consensus nodes. So by moving this, the block nodes allow us to move the state information, move the state information off of consensus nodes onto block nodes, and then they can take on this responsibility of having these snapshots. And the snapshots are important for disaster recovery.
And also, if you want to be able to bootstrap a mirror node from the state now rather than having to read the entire history, and those snapshots should enable that. There's a whole bunch of interesting use cases to getting a snapshot in time, as well as being able to get the entire history. And I think the other big thing of this was to try and make all of the data public, fully specified, and as clean and sensible as possible. And that was really a big strive. So then looking at sort of, so block streams, so, two things came out of this whole sort of investigation, block streams and block nodes. So the first thing is, block streams, which is what's the format that the consensus node is going to push out. And so, the first thing, as Richard mentioned, is streaming. So the idea was this is a continuous stream of data. You can chop it into block files if you like, but you can also have it as a continuous stream of data. So we can get rid of a lot of the latency problems. The other thing that is a massive thing is every block has the full proof of the network. So you don't need to go to multiple consensus nodes data to get the full trust of the network. You can just take any block from any node and you'll get the full trust of the network. I love Richard's analogy of, you could take that block, write it onto stone, stick it in a mountain, come back a million years later, and still fully trust everything that's there.
Yep, you could totally prove that that was actually produced by the consensus nodes at the time.
So,
and I think that like on the streaming, you think like, what impact can this have on latency? Today, there's like a 2-second built-in latency into the system because we process a transaction, we produce a record file once every 2 seconds, we upload it to Google Cloud, AWS, and then the mirror nodes download it, then they process it, the whole block, then they ingest it into the database, and then it becomes available. And when you think of it that way, it's a miracle that we've got this thing going 7 seconds from the time that you submit your transaction till it gets to the end.
And there's multiple polling steps in there. It's
Yeah.
just far from optimal. So this should be push streaming end to end, minimize. There's a whole bunch of steps we went through in the design to minimize latency. Until we get out into the real internet with all the pieces in place, we won't know the exact latency. But we're really trying to cut that down.
Yeah, you can really imagine that if instead of waiting those 2 seconds, if you're just sending out each transaction's results as they're happening, and they go to the block node that then goes to the mirror node, which is building up its transactions to update its database, you should be able to cut a lot of time out of that whole sequence. So
Yeah.
that was really an important part. Was to a lot of the design is fundamentally about being able to stream these little pieces out there.
Another piece is, I worked in, currency exchange trading and trading where, latency matters. So what I really wanted to do, so I think there's a whole bunch of applications where getting low latency access, even just the simplest, I was chatting to someone from Hashgraph and was saying, if your wallet, how quickly can your wallet tell you your transaction's complete? Even that latency hurts us. So I think the shorter the latency we can have and the quicker you can have, that opens up more use cases. So the idea here was to get the latest update to your account to your DApp as fast as possible, and in a fully trusted way. And the last one was deduplication. That at the moment we have 31 consensus nodes producing record streams. We have to later on go back and deduplicate that data and deal with the fact there's duplication and store multiple duplicates, which costs a lot of money, upload multiple duplicates, that costs money. So really, a lot of this is also to try and reduce the costs of running the network so that it's better for the future and maintainability and so forth.
Yeah, it really feeds into that scalability of the consensus nodes. When you're trying to get to, more than 10,000 transactions per second, like what's the limit? It's not the Hashgraph algorithm, it's bandwidth. So everything we can do to save bandwidth comes back to help us.
Move on.
I don't know. We could just look at this slide for a while too.
I was trying to move on to the next slide, but
It's not doing the next.
no. There we go.
All right, there we
go.
go.
So block nodes. So what are the advantages of block nodes? Why did we add block nodes? Number one was decentralization. The second one is because we're sending the state out, block nodes can now have a copy of the same state that's in the consensus node. So therefore we can offload responsibility. So like we talked about, they can create save state backups. They can create state proofs. That they have full trust cryptographically. They can provide that at low latency. They can provide low latency access to data. So all the sort of queries you could do, like what's my balance, you could do that with very low latency against a block node.
This was really key in the design, was the idea that the state was going to transfer along with the block node. So you can, you have some Merkle tree on your consensus node. If you're consuming the block node stream, the block stream, you can construct the exact same Merkle tree state on the receiving side. You could rehash it, you could verify it, you can check everything. It's all there. Everything that you need is right there because you transmitted that state.
You can kind of think of it, I kind of think of the consensus node's state as like a goldfish. It has, it knows the last 10 seconds of what's happening. It knows everything about the world for the last 10 seconds. So it knows every account balance as it was in the last 10 seconds. And so the idea is we can take that sort of brain of the consensus node, transfer it at low latency to a block node, and it has all of that information available to it, so it can answer all of those questions, plus it could potentially store it for longer periods and do interesting things. I think there's lots of cool things we can build on.
You mentioned the monetization model?
No.
I think I interrupted you.
Yeah. So there was one more thing, which is, block nodes can have monetization, and we'll go into it later in the deck of the details of that. Both in terms of the consensus, block nodes run by the council members will have a monetization model, and also, if you run your own block node, you can do your own monetization model and charge customers for it. And there's a bunch of interesting upsell services that people can build on block nodes and provide out to people. So let's have a look at what does a block stream actually look like in the data. So this is the block stream. So the key thing here is it's non-hierarchical. It is hierarchical, but it's not sent as a hierarchy. So we have the block header, which denotes the beginning of a block. So this is the beginning of block 1, and there's the beginning of block 2 over there, and the block proof is the end of the block.
Okay.
So the block is everything contained between the block header and the block proof. And then we also have round headers, which contain the consensus round. So there's a round header that designates the beginning of each round. There's event headers that designate the beginning of each event. And then there's a transaction which designates the beginning of each transaction and all of the items that come as the outputs of that transaction. And the reason why it's non-hierarchical in terms of the stream is as soon as we get to this transaction, we can send it out. So we can send this data out with the minimum amount of latency possible. So as soon as we have that piece of information, we can send it out. And so the idea was to be able to send this stuff as soon as possible, and then block nodes can work on it as soon as it arrives, even if they haven't got the proof yet. So as it's coming off the wire, we can be processing that data. It's all about reducing the latency and trying to get the information to people as fast as possible. So that's sort of the basic idea. So one of the important bits is, we're changing from where we are today to block streams. So today we have record files, and how do we make that transition, and how do we mash those two together and make it as seamless as possible? So one of the abilities of block streams is to contain wrapped record files. So we can't go back and rewrite the history of the network that's been assigned. That's just not something possible with blockchains. But what we can do is take that data in its existing signed format and repackage that into an easier to consume format. So we'll take each block, we'll gather all the information from all the nodes, put it together into a block stream format with the entire proof needed for all existing blocks until the point that we transition to block streams. So in the future, you'll be able to go to a block node and get any block from block 0 at Genesis, the network, OA launch of the network, all the way through to the latest block. And there'll be two different formats, the new block stream format and the legacy record stream format with its sub-formats. So we would like to have gone back and rewritten history, but I just don't think it's feasible. It's something that could be done in the future, that some future point could sign that and give trust to it. So yeah, if there's enough interest, I think that there could be an opportunity there. But for now, this is the plan moving forward. So how do you understand the trust and proof within a block? This is something that's kind of complicated, but complicated for very good reasons. And so we have that very nice linear set of data of all of the items that are in the block. How do we construct the proof of that? So what we actually have is we actually have multiple Merkle trees within the block stream. So different subsets of those items get built into different Merkle trees. And the reason why we have multiple Merkle trees is it allows us to remove or filter out parts of the block stream for downstream consumers very efficiently. So if you only care about transactions, we can give you just transactions. If you only care about event information, we could give you just event information. If you don't care about one of those, we can filter it out. It also allows us to do things like include the previous block, which forms the actual blockchain, and include state. So yeah, we're talking about that sort of model of the memory of the consensus node. At the beginning of each block, the state of which that block builds on is also included within the hash of the block. So you can actually create proofs based on any part of that state. And the whole of this gets formed into a single root hash of the Merkle tree, which is then signed. Now, most of you probably won't need to deal with this. It's only really if you want to write code to be able to verify the proof of a block node, of a block. But if you wanted to be able to self-prove the contents of a block, you'll need to understand this, and we go into great details in the HIP. There's also a sample streaming algorithm that allows you to compute these Merkle trees on the fly as the data arrives, not having to wait for the entire block to arrive to do all of the maths. So it can be very efficient.
And when we talk about input items and output items, if you remember back to the original diagram Jasper had, the input items would have been like the transactions and the events and the rounds that came out of the Hashgraph.
So the input items is everything that's going into the Hashgraph and into execution, and then the output is everything that was done during execution. So it's the output of the transaction plus any state changes that are made by that transaction. And we'll go into that in some more detail. So, anybody who's familiar with a blockchain, this shouldn't look too crazy, but basically this shows us how we create the blockchain. So we have the single proof on the latest block, which is proving the contents of that block, the contents of state at the beginning of that block, and the previous block, because its hash is included.
Yeah, this is the hash of that tree.
Yeah.
And that has the hash of the next tree, and so on.
So actually, a signature on a single block proves the entire history of the network. And so we actually go all the way back to the very first block stream that we produced, back to the record stream. So the first stream block ever produced will include the hash as a starting point at the end of the record stream, and goes all the way back to the Genesis null. So you'll actually be able to prove with the latest block signature the entire history of the network, or any point anywhere in that. And so that's an important property. So I think state changes is probably the most useful new piece of data that's going to be available to people. If I was a dApp developer, this is the bit I would care about. I think this is the most interesting. To get it today, Miranode has to collect all kinds of bits out of the record stream and try and reconstruct state, and it still doesn't have all of the information it needs. So, for an external application to be able to know what is inside the memory of a consensus node, that isn't entirely possible today. And this not only makes it possible, but hopefully makes it easy and simple to understand, and lets apps start to use that in their own work. So there's two different conceptual levels for people to understand in this. And again, I think most people won't need to go into the details of this. It only really matters to people who are trying to create state proofs. So if you're going to go down trying to create state proofs, then you'll need to understand these two levels. So the first one is all of state, that whole memory of the consensus node, is one giant key value store. It's a binary key mapping to a binary value. So it's just one giant key value store. And accounts, tokens, everything is stored in that giant key value store. And then we have an abstraction layer on that, which is the states API, which makes it much easier for people to consume. So the states API takes that massive map and segments it into smaller data structures of different kinds for different purposes. So like accounts is a separate map, or tokens is a separate map, or smart contracts, or the key values. So it splits it up into that concept. And state changes, as you get them in the stream, are at this high-level concept. So when you see a state change, it should be much easier to understand. And
this was one of those simplifications, was to break all of the complexity of everything that you have in state down to these three types. And to basically store it in one big binary Merkle tree.
Yeah.
But it's really, you work with it as if it's just simple maps, or lists, or just single.
And the reason why there's the two conceptual levels is one is optimal for performance and one is optimal for understanding. And so we're trying to both make it easy for people to understand and use the data, and optimal performance for the consensus node to execute, and also simplicity of code in the consensus node. One of our challenges is, the simpler the code can be, the less chance there are for mistakes, and the most flexibility we have. So we're really trying to get that to be as simple as possible. So when we're looking at it from the mega map point of view of this great big binary tree, there's a big binary tree of internal hashes. Along the bottom is all the leaves, and they're totally intermixed. There can be any kind of entity anywhere in that tree. So you've got accounts, tokens, smart contracts. You have key value pairs of smart contracts. You have singletons, so we keep things like the most recent state of consensus and the most recent state of producing the block stream. And that's important for consensus nodes that need to connect back in. So, if you reboot a consensus node and it reconnects in, it needs to be able to catch up with the latest information, so that needs to be available to it. When a node starts up and joins the network, the only thing it needs to know to participate is the current state.
I like this. There can be billions of leaves. This is a really, really big tree.
Yeah.
It's a really big tree.
Yes, this is a very simplified view. At 1 billion, we end up with 30 levels up here. And this will be the 31st level. And it's a balanced binary tree internally. So then, when we look at this from the state's point of view, it's a much simpler concept. That we have a number of different named maps. So we have accounts, we have tokens, we have contracts, and we have key value stores. And there's a bunch more of these. And then we have single objects or singletons, like the block information. And when you get something from the contracts map, you'll just see the contract name, and it maps to the contract object. So it's just very simple, or your account ID maps to your account. So at this point, it's just very obvious. It's the same thing you'd look at if you looked in Miranode or Hashscan. It should be pretty obvious. It's talking in terms of the high-level business concepts as opposed to the low-level implementation. So every time we touch anything in that big tree, at the granularity of a single transaction, so if your account is updated 100 times within one transaction, we'll only provide you one state change. So we had to pick some level of granularity to make this make sense, and the granularity we store data at is a single transaction. If you call a smart contract which calls other smart contracts as sub-transactions, it's the granularity of the super transaction. And so each transaction will produce a list of state changes, and those state changes are in terms of simple sort of CRUD operations on those high-level states. So we're either adding or removing a whole state type itself, like we're adding accounts to or whatever it will be, or some other new thing. We're updating a singleton, we're updating or inserting a new value into one of the maps, we're deleting something from the maps, and we also have queue states. There's a couple queue states that act as a big queue, and so you're popping and pushing things from those.
Yeah, and I think this was a very interesting problem when we were going through the design for block nodes, and we're kind of debating it. There was a big debate over how do we represent these state changes in the block stream. And we kind of went back and forth between two different options. One was basically state diffs, and the other one was to just put the whole state in there that had changed. So like on the previous slide where he had like an account object, if you change the account, do we just put in what changed on the account, or do you put the whole thing in there? And there was the challenge is that you get fewer bytes on the wire if you just do the diff. But if you wanted to understand what that account state was, you would have to traverse more blocks in order to try to coalesce it all together and to have a single view. So what we decided was that we were just going to take the full object and stick it in the block stream so that you could actually start at the most recent block, the latest block that existed, and you could work your way backward, and the first time that you encounter your account, it's going to have all of the latest information. You don't have to go any farther back. So this makes sense to us because your blockchain can be, we're generating a lot of blocks, right? Every 2 seconds there's a block, and in the future maybe it's every second or every half second. You're going to end up with a large number of blocks. And if you had to traverse the entire chain in order to try to figure out what your account balance was or something like that, or the state of your account, it could be quite onerous. So instead, we wanted to have this idea that every time that the state change happened, we had the whole state. And that meant that if you were doing, like, say, an app that was consuming the block stream, you could just take that piece and stick it in your database. You don't have to try to merge things together or anything else. So we try to make this, we decided to spend a few more bytes on the wire in the hopes that compression will help us in exchange for a better experience and to make it more foolproof for people who are building applications using this.
Yeah, because it's a complete nightmare. If you had 100 fields on your account and each one of those changed once a month, each one of them changed in a month, you'd have to go back 100 months worth of block streams to be able to reconstruct a full picture of your account.
Yeah.
So it quite quickly becomes unmanageable amounts of data you'd have to scan through to construct a single account. And this is why Miranode has to scan the entire history today to be able to fully reconstruct all of the accounts. It has
Right.
to.
So if you bring a mirror node online, you have one of two options. One is you download an 80 terabyte file as your starting point. The other option is you start processing the record streams from the beginning of time. Both of those are kind of awful. So what block streams will enable is a third mode for mirror nodes where you can just start from the latest saved state and then you can rebuild going in reverse. You just actually traverse the blockchain in reverse, and each time you encounter a account or something like that, you put it in, and then you don't have to process that.
Or as a company, if you know all of the accounts and contracts that I care about didn't exist before 2025, then I only need to start processing blockstream from 2025. I don't care about anything prior.
So your mirror node has a way of being able to come live immediately and then get filled out with historical information, but at least you can come live immediately, which is a big advantage.
So how can I use these state changes? I think we've all talked about this, but really it's low latency access to the knowledge of the consensus node available to dApps. And it also allows people to maintain state. So this is something that, Ethereum is quite easy. You can run a node that replays the transactions, build your own live state, and you can have your own local node that is in sync and query. That was something very hard for us. And the reason why it's hard for us is the size of state and the rate of change of state. At 10K TPS, we can change like 250,000 state values a second. So state can evolve at incredible pace, and state is many billions of entities. So it's just a totally different league of scale. So the simple answer of just, I want to run my Raspberry Pi and keep up with this just isn't possible. So we had to come up with other ways of how can you have access to that data in a convenient, low latency way, but will also scale. And really that's what the aim of this is.
Yeah, exactly. So you don't have to re-execute the transactions or reprocess the gossip in the Hashgraph. You can just get these state changes, apply them to your local state, and you're good to go. So even on lower powered systems. Again, the main problem is the bandwidth. As long as you've got the bandwidth for slurping in the amount of data that's coming in, then it doesn't take a lot in order to keep up the latest.
Yeah, and the compute shouldn't be high to consume those. You don't
Very
have
low.
to re-execute all the transactions. You can just take the outputs of the transactions and fully trust those with the signing and apply those to a local database. And the last bit is we can actually also use these state changes for starting up consensus nodes. So a new consensus node comes online, or one's rebooted, or the software upgraded, etc. It needs to get its latest state to be able to start working on the latest transactions. And to do that, it can use these stream of state changes coming out of the block stream.
Yeah, so I think probably worth a couple minutes on just what reconnect is. So reconnect is what we call the process of a node that's kind of behind all the other nodes. Maybe they're 5 minutes ahead of this node, or maybe they're 3 days, or maybe I'm a brand new node. Somehow I need to get all of the state that those guys are using so that I can, when I'm gossiping, I'll be able to apply those transactions and get to the new state, right? I need some method of doing that. Today we use a very clever method for doing this where each consensus node will look to another consensus node and say, hey, brother, will you please help me out? And he's like, yeah, sure. So now I'll be the learner and Jasper's the teacher. And I'll tell him, I'll say, okay, well, my current Merkle tree starts with this root node, the hash of this root node. What have you got?
And I'll say, it's either the same or not the same.
Yeah.
And then there's this ongoing conversation backwards and forwards.
Where we're just trading hashes, and then eventually we figure out exactly which leaves are different. He sends me his leaves. I apply them to my side. And if we did that fast enough, then I've reconnected and I can start gossiping and life is good. If we didn't do that fast enough, then we go back and do the whole process over again, hoping that each delta is a shorter time period than it was before, and then we catch up. The problem with this system is it takes bandwidth and compute from both sides. It takes resources from the teacher to help the learner learn.
So one consensus node is paying to teach another node. And it's actually really quite painful for it because it has to teach from a consistent point of view. So at the point where Richard asked me to reconnect, I have to fork my database, keep a constant view to be able to synchronize with him, while still maintaining my own database and keeping in sync with all the others. At 10K TPS and doing everything else. And so I have to have enough memory on the consensus node to be able to handle two databases at once.
Or, yeah, or more, depending on how many people are trying to reconnect with
Yeah.
you. So instead, we said, hey, this is brilliant. Now that we've got the state off of the consensus nodes, we're putting it in these block streams. I mean, it's being replicated in the block stream. And a block node can apply all that state on its side. It has a Merkle tree. Well, that's great. I can now do a reconnect with a block node instead of doing a reconnect with a consensus node, which means that my consensus nodes are never put under pressure. It's just because one consensus node has fallen behind, it doesn't impact the others. They just keep on cruising, happy little campers.
And all of the RAM and hardware in a consensus node can now be dedicated to consensus and execution, which is what it should be, and not teaching other nodes in the case when they have to restart.
Exactly.
We don't have to keep a whole bunch of spare hardware just for the cases where nodes have to restart. And the other thing is, block nodes can scale out horizontally, so we can have an infinite number of block nodes and plenty to be able to teach consensus nodes from and scale out. So as we scale out to community nodes and more consensus nodes, there's going to be plenty of sources for them to get their data without endangering the other consensus nodes.
Exactly. And there's also some new interesting reconnect algorithms that we can use with block nodes. Instead of the tree diff system, we could also do one where we just replay and apply the state changes. Like, okay, just I went offline 5 minutes ago. Please start streaming me the changes. I just apply them, and then I'll catch you.
Yeah, I can just send you the last 5 minutes of changes, and you apply those. There's going to be some duplication in that, but I don't have to do any thinking to be able to produce that. So it's very cheap for the block node to be able to work out what to send you, because you just say, I'm at block 1000. I know block 2000 is current. Please send me the differences between those.
Yep.
So this was just a very, very high-level idea of how could you use this in your DApp. So going back to how can I take the block stream and use it. So I would go to a block node and subscribe to the stream. I can subscribe to either a full stream or a filtered stream. We haven't talked about filtered streams yet, but filtered streams is where you can say that this is just the set of accounts that I'm interested in. This is the smart contracts I'm interested in. Only send me transactions that are affecting those guys, so I can actually get a subset. I kind of think of it like the old Twitter Firehose API. It was very much inspired of that. The entire data set is absolutely massive, but some people only care about a subset and only want to pay for the bandwidth for a subset and to get the data for a subset. So filtered streams allow that. So you pick either the whole thing or the subset you care about, you subscribe to that, and you can start from any block. You can either start from a historical block or the current live block. If you start from a historical block and catch up, we'll transition you automatically onto the live block and just keep on pushing it as data is being produced by the network. So you've got this constant stream of state changes being sent to you about just the stuff you care about. So once you've got those stream of state changes, you can then just pull out the bits you care about, stick them into any key value store. My aim for this from the beginning was like, I should be able to write like 100 lines of JavaScript code or any other language of your preference to be able to subscribe to this stream, pull out the key values I care about, the accounts, the smart contracts, the tokens, and shove them into whatever database of choice. I can stick it into Redis, whatever I care about, and then serve that out to my other app functions and out to my customers.
Yeah, so going back to that idea of those two, there's the view of the world of a big Merkle tree, and then there's the view of the world of just simple key value maps. If you are not trying to rehash the Merkle tree to verify proofs and all that, and you're just, you just verify the signature on the block and you say, good enough for me, you can just take things at that key value map level and shove it in here and you're done. You don't have to know anything about our big complicated Merkle trees. You don't have to know anything about the whole blockchain and hash sequences and everything else. You just literally take each one of those state changes that's in the block stream, stick it into whatever key value store you want, and then now it's available.
Yeah.
And because we sent you the very latest version of each entity as it changed, you don't have to merge it with anything that's in here. You just throw it in.
Yeah. One of the big expenses for Miranode on Ingestion's day is they have to do upserts. So they have to take, because they're only getting deltas, they have to read back from the database the existing current value, merge in the delta, and then write it back to the database. So they have this endless read-write cycle, where in this case we're providing you the entire object every time. So it's just straight, just as it arrives, write it in.
And this could be like a Redis, or it could be a database.
Yeah, RocksDB, a SQL database, take your pick, store it in RAM. If I'm only interested in 10 accounts, that's all my business cares about, I just stick it into a simple map in memory, And so the whole idea of this is to get you the bits of data that, your business needs with the lowest latency possible and the lowest bandwidth cost and everything else to get, the lowest hassle on the network and the lowest hassle for you to get it there, really.
Yep.
So let's have a look at sort of a deep dive into sort of block nodes a bit. So this is sort of a very high-level internal architecture of block nodes. And I don't think this matters to most people. It's more of a sort of curiosity. But one of the key points of block nodes from the block node implementation that we're creating is it's going to be modular. And modular in two ways. Modular in terms of it can do 10 things, and you can choose which subset. If you're running your own block node based on our code base, you can choose which subset of those you want to run. So you can choose your own data access, what facilities you have versus cost. You can pick where on that trade-off you have. And then the second thing is to add the ability to generate third-party plugins. So the block node is ingesting, verifying, and storing all of the block information, and then you can access all that information. And so you can add your own plugins in here to provide APIs to get any kind of interesting data out of that you care about.
I thought that was an interesting thing you said. If you use our code, you don't have to use our code. You could go write your own block node in whatever language you want to deal with it how you want. There's just a gRPC APIs that you support, and nobody will know.
Yeah. Yeah, and the nice thing, gRPC is gRPC basically has, a definition of protobufs for all of the objects involved, and it has a definition of the API of the service endpoint and each of the endpoints provided. So you take that schema definition, you run it through the Proto-C compiler from Google, and it will generate you an implementation in the language of your choice. So we can take that one schema, and you can generate it into any language you like, and then from there you've got the data, and you can decide what you want to do with it. And we're doing this inside of Java, and building it on a lot of the same technologies that the consensus nodes is built on, partly with the aim to try and make this as efficient as possible. That we want to be able to run on as small a hardware set as required and serve as many customers as we can with as small amount of hardware as possible, because that changes the economics of the game. And the cost of other people getting the data is based on the cost of running these nodes, and if we keep that down, then it makes it very cheap for everybody to get the data. Yeah. And so these are some of the APIs we're going to provide, and we'll look at a few of these in more detail in a second. But the main thing is the streaming ones, the one we talked about a lot, but there's also going to be random access. So I just want to go back in history and get block 50. I can just ask for block 50 or block 0. And just go and get any random single block. I can check the status of block nodes, is it up and running? I can ask for proofs. So I can ask for any piece of either state or any of the contents of a block. So whether it's the transaction or the outputs of the transaction and ask for a concise proof of that.
I want to have some kind of cryptographic proof that my account balance was X on such and such.
At this point in time, yeah. Yep. There's going to be billing, and we'll go into that in more details, and then there's also going to be an API for accessing the state snapshots. So the streaming API, I think we've gone through in most details. I think this is what most people will probably use. It's probably the most useful, and I think the coolest part of it really is it pushes data to you, and you can start at any point. You can either start with current live, or you can start at any historical point, catch up, and carry on with the future. And if you are too slow consuming the block stream and fall back behind live, then you will just go back onto historic data and then move backwards and forwards. So we can deal with the fact that different consumers are running at different paces. Because that's another very key constraint here, is that if we've got 1,000 people consuming off a block node of the stream, they can be consuming at very different paces. And so we need to be able to deal with the fact some of them might be running over a cellular network that's coming in and out or whatever else. We need to be able to deal with people at different paces. So it's very much design.
The other thing about the streaming endpoint that's important to understand is that you remember in the previous diagram, it's like the block header, and then way at the end is the block proof. If you're on the streaming guy where we're streaming those block items to you, you're going to be getting items before the proof. So it may be that when you get to the proof, maybe the block node that you're working with is being dishonest or broken or something. Maybe you never get the proof. So if you're using this streaming guide, this particular one, where it's streaming you items, because you can also do a streaming one where it streams you an entire block at a time. But if you're doing the one where it's streaming you items, you have to be prepared to sort of throw away that block and start over again.
Yeah, and as a consumer, you can either do the sort of dumb simple answer of I'll just store all that data up until I've got a complete proven block, and then I'll start processing it. Or you can do the optimistic compute answer and say, okay, well, I'll create a new transaction on my database. I'll do all of these updates and inserts, and I won't confirm that until I get the proof.
Yep.
But that means I can do all of the pre-work ahead of time before getting the proof. So it all comes down to that idea of lowering latency and trying to get.
And this is where we're hoping to really tighten things up, where from the time that one of our consensus nodes handles the transaction to it going to a block node, to getting streamed out to a mirror node, and having those three close to each other, then the mirror node will get it, do all the pre-work. By the time the block proof shows up, the mirror node's probably done everything else, and we've eliminated almost all of the additional latency that comes in transmitting this information to the mirror node.
Because the mirror nodes today are SQL databases behind the scenes, and they have to build up a bunch of inserts and updates and upserts. Hopefully in the new thing, that will just end up being a whole bunch of update inserts, and they'll be able to produce that whole SQL batch before they get the proof, and the only thing will be the final commit that happens the proof. So that hopefully that will really lower the latency of the data availability to mirror node customers as well. That was definitely one of the other things we're trying to design out of this. So the proofs endpoint. So we talked about this briefly, but I think this is another area that has huge opportunities for ecosystem people. And basically it's the ability to be able to create a concise proof of any of the pieces of data. And we said there's two kinds. And that proof is basically going to contain the piece of data itself, a bunch of hashes, and a signature. And you'll be able to verify that. And you'll be able to prove from that the supermajority of the network agreed at that point in time this was the piece of data irrefutably.
And we very intended, there were several different schemes that we looked at for these proofs, but we settled on ones that would work well inside, where the verification of the proof happens inside a smart contract. So you should be able to take one of these proofs, take it to another ledger or Hedera itself, pass it to a smart contract, to be able to verify that proof.
And one of the aims of these proofs is to be able to build into ledger communication systems on top of that and make that efficient. The proofs might be too big or cost quite a lot of gas today, but you could also apply a ZK step after this to take those proofs, compress them way down. So if you'd rather pay upfront cost to compress it versus downstream cost verifying it, you can choose that trade-off. We're not pushing you down one path or the other. You can choose the right trade-off depending on the use case you're at. And you can extend block nodes to add ZK support. And I think creating a block node producing ZK proofs will be a great upsell opportunity for the community. I think there'll be some interesting people who want that and don't want to have to build it themselves. And
I think that the block contents proofs, at least to me, when Jasper came up with this distinction, was, I thought, brilliant, because we've always talked about state proofs, and what that just means is that in your Merkle tree, there's some state in that tree that you can prove was in that tree. But a block content proof, we have some things that are not in a Merkle tree. For example, if you have a HCS topic, that's in the Merkle tree, but when you submit a message to the topic, it's not in the Merkle tree. It just goes right out into the blockchain, and that's where it lives. And block content proofs allow you to prove that that message was in a block that was produced by the consensus nodes. So it's kind of an interesting distinction. You can generate a proof that this is in that Merkle tree of state, or you can prove that this is a part of the block stream, which is particularly useful.
Yeah, and really a lot of that came out of how there was a bunch of interesting use cases about proving the contents of HCS streams, or I just wanted to prove that my transaction existed in the block stream. I don't care about the account or anything else. I want to prove that actual transaction exists in the block stream at this point in time. Or I've got two transactions. I want to prove this one was executed before that one. There's all kinds of interesting ideas you can build on that. So let's briefly sort of look at monetization. So this is how can block nodes charge people for accessing their APIs and their data. So the primary reason that we need to do this is block nodes need to be able to, stop people abusing them, basically. It's a prevention of abuse of the block node. That, if the council runs, 10 block nodes, then we don't want people to be able to just use up all of the resource in those 10 block nodes and prevent the rest of the community being able to get access to the data. So we need some way to incentivize people to use them sensibly. And this is primarily true for the council-run first-tier block nodes. After that point, people can choose to give the data away for free, charge anything they like. It's totally up to them. So we're thinking that there's potentially sort of 3 modes for block node billing. There's going to be the standardized Hedera billing, which is what the council-run block nodes will use. There's going to be, just provide it for free, or, one of the use cases I think about a lot is I'm going to run a block node inside my own data center or inside my firewall, and then have 100 other servers of my own accessing that, and they don't want to pay for that data. I pay for once for that data to get it inside my network, and I pay for the bandwidth once, and then I have 1,000 servers that go and use that, or 1,000 Amazon Lambdas that go and serve off that data. Or, I want to provide it for free to my customers. Totally up to you. Or you can set up custom billing. You can have an API key, bill per month, do any kind of billing you'd conventionally like to do. It's totally up to you if you're running your own block node, if you want to bill or how you want to bill. Or you can provide standard Hedera billing from your own block node that you're running as a community member, and then other people can use your service in a very well-known, friendly way. So that's a way that other people can provide block nodes through the same billing mechanism. And we'll have an address book of block nodes, so people can just go out there and find any block node, either a council one or any community one, and then use it through a standard billing mechanism and know how to access it.
Yeah, don't forget my favorite, that last bit.
Yeah. So the aim is, we'd also like to do a low-speed gossip network coming out of the block nodes to allow people to just get the data for free. So, if you care about low latency, then you can subscribe and pay for it. If you don't care about low latency, you just want the data, you're just doing it for a hobby, whatever else, that latency doesn't matter to you, then there'll be a gossip network. This isn't going to be phase 1, but it's definitely the intent over the long run to support a gossip network between block nodes.
And once we've implemented that, there could be millions of block nodes. Just as many as is necessary for the world can be run, and it won't put extra pressure on the council tier 1 block nodes. They'll just be able to gossip to a few peers who gossip, and it goes out into the world.
Yeah.
But like you're saying, if you want that low latency streaming thing, either you're going to pay for it, or block nodes will be set up with some type of a firewall, or they're just going to play with fire and hope for the best.
Yeah. And our hope is that the latency of the stream passing through the block node should be in the milliseconds.
Yep.
So you shouldn't be paying very much latency of bouncing through 1 or 2 milli. It's much like a router on the internet. It really shouldn't be adding a lot of latency. Yeah. It's pretty much just taking the bytes in, passing them out to 1 or more consumers. There's no reason for it to be slowing things down. So whether you're getting it from a tier 1 block node or a tier 2, it should be a few milliseconds of difference. It really shouldn't matter. So how does Hedera standardized billing work? Kind of the idea of this was to try and do it sort of Starbucks card style. So if I want to get data from a block node, I will go onto mainnet, I will do a transaction from my account to the block node's account and say, send it 20 HBAR. The block node will see that a transaction of 20 HBAR being sent to it from a known account, and it will then put it into its internal database and say, okay, you have 20 HBARs worth of credit. And then when you access the block node, you'll authenticate yourself through OAuth. You will sign using your same public-private key as the account on mainnet, so all of the block node accounts are mainnet accounts, and it uses the same accounts. You might want to create a dedicated account for this, or not, it's up to you, but use the same accounts. And so you'll then authenticate yourself with your account. It will say, okay, I know that this account, you are the same person as this account on mainnet, you have 20 HBAR credit with me, and as you start pulling down data, I will debit from that 20 HBAR until you've spent all of that 20 HBAR through buying services. And then you'll get a message saying, you spent all your money, and then at any point during that, or ahead of that, you can top up that account with more money. So the reason why we did it this way, the first question everybody asks is, why didn't you just do a transaction on mainnet for every time somebody accesses something from a block node? But if you think about it, if people are reading for every block, it's a massive amplification stuff. So, if for every block there was, 1,000 consumers, then that's 1,000 new transactions on mainnet. If there's 10,000 consumers, then that's filled up the entire bandwidth of mainnet, just people paying for people to hear other people paying for people. So it just doesn't scale out at all. So the idea is sort of nano payments. It's like, how can we enable nano payments and keep the cost on mainnet, keep mainnet bandwidth available for real-world use cases, and not clog it up with people paying for the data. And then the other part of the sort of standardized billing is there will be a standardized API for the price sheet. So there'll be a standard billing model of this API call will have so much base charge plus this upcharge, and that will be standardized. But what the values of that, of how much HBAR each of those cost, will be totally up to the block node provider. So different block nodes will be able to charge different prices for their services. When you go and look at the address book, you'll be able to choose based on price or other decisions. So the big question everybody else is going to come is, when's this going to be available to me? When can I start playing with this? So block streams are in preview today. So if you go to the public buckets, you can get the block stream record of mainnet today. Those blocks are not signed. They don't have any authority, but all the real data is there. So you can start prototyping apps, playing with those. We really love people to try it out. Any feedback now is much easier for us to change than later on. So the whole idea of this preview stream was to get people to be able to play with it early. And this has been running since late last year. Then we will finalize the HIP. So when the HIP process finalizes block streams, and then there'll be the big switchover date when we switch over from record streams to block streams. And that will likely still be block streams in buckets, and that will continue for a while, and then we'll roll out block nodes as stages after the point that block streams are available, to the point where we do the big switchover that blocks will no longer be available from buckets, they'll only be available from block nodes. But this allows us to have a few stages where block nodes are not in the critical path, because once we get all the way to the end, block nodes are critical for the network success. The only way you'll be able to get information from mirror node is if block nodes are running. So we need to be 100% sure they have the same uptime and availability as the rest of the consensus node network. So this allows us a bit of a gradual process. Hopefully we won't make any mistakes, but if we make mistakes, they won't cost everybody. So that gives us a chance. And the hope is for us to get that out towards the end of the year, and we'll see how that goes. We'll try for much sooner, but there's still a bunch of thing happening in terms of the features on both of these.
And the mirror nodes that are out there in the world have to switch over as well. They have to upgrade to the latest mirror nodes. There's a lot of dependencies that we have to roll out, so we'll just do it really carefully.
Yeah. The rollout is both absolutely mission critical and it affects a lot of other everybody who runs third-party mirror nodes. So we're going to have to get everybody together and control this. So it's going to be a big coordinated effort to get through this change. But you should already be able to start playing with this and start thinking and dreaming up cool ideas based on it now. So I think we ran out of time for questions, but you're welcome to find us. We'll be out here, so come and find us and ask questions, and thank you.